Okay, so let's look at theorem 9. So it says if yp is a particular solution of the differential equation y double prime plus p of x y prime plus q of x y equals g of x, where g of x is not equal to the zero function, then the general solution is given by y equal yp plus c1 y1 plus c2 y2, where y1 and y2 are solutions of the associated homogeneous differential equation. And the associated homogeneous differential equation just means replace the g up here with 0, which I've done here. Okay, so let's look at the proof. Okay, so we're going to let y be any solution of the non-homogeneous differential equation. So this guy up here. So it's called non-homogeneous differential equation. So when the g is not 0, we will now show that our y minus our yp, again yp we're assuming is a particular solution of this differential equation up here also. We're going to show now the difference of these two solutions is a solution of the associated homogeneous differential equation, so this guy here. Okay, so let's make some observations. So note now, well, since y is a solution and yp is a solution, it means that when I put y up here, I'll have y double prime plus p of x y prime plus q of x y equals g of x, and also yp is a solution. It means that yp double prime p of x yp prime plus q of x yp equals g of x. Let's subtract these two equations. So subtracting the two equations we get then. Okay, so subtracting these two equations, we'll have y double prime minus yp double prime here, and p of x y prime minus p of x yp prime I got here, and then q of x y minus q of x yp, which I have here, then g of x minus g of x. So g of x minus g of x here would be 0. Okay, so I'm out of space here, so let me erase a few things and we'll keep going. So we have to here then. So let's factor the p out of these two here and the q out of these two. So doing that we get then. So we get this then, factoring the p and the q out. Now next thing to note is that y double prime minus yp double prime you can write by properties of derivative as just y minus yp double prime. And this you can write it just as y minus p prime. And this one's already fine. So let me note that here. Okay, so we have this then, and this shows that y minus yp now is a solution of the homogeneous, so the differential equation equal to 0. So let's note that here. Okay, so we have our y minus yp is a solution of associated homogeneous differential equation, just means where it's equal to 0. So by theorem 5 now, we know that the solution of this associated homogeneous differential equation will be linear combinations of y1 and y2. So hence we can say the following. So by theorem 5, so theorem 5 is basically talking about the homogeneous differential equation when it's equal to 0. We know that the general solution is given by c1 y1 plus c2 y2. So therefore y minus yp has to be some combination of these two vectors for some c1 and c2. Now we can just move the yp across the equal sign and we're done. Okay, so adding yp to both sides, then we have our y equals yp plus c1 y1 plus c2 y2. And that's what we're trying to show, so hence claim follows, so we're done. Okay, so we're done with the theorem. Let's leave the video here.